Objective 3.5, Parent Functions. So chapter 3 is a little bit different than a lot of our other chapters because there's really almost two distinct parts to it. In the first part that we did up to our first quiz, we were looking at a specific type of expression, an equation, which is that when we have radicals or exponents with rational numbers. But then the second part of our chapter kind of expands to more of a global view on functions, not just one function in particular, but some things that we can do with functions in general. And so in order to understand what we're going to be doing in the second part of the chapter, it helps if we understand the idea of parent functions. And so that's what today's lesson is about, and that's what your activity, your pre-lesson activity using the TI Inspire was all about. So, what we want to be able to do is identify and graph parent functions of the following families of functions. So we've got linear, absolute value, quadratic, cubic. For some reason, square root didn't come out here, but that should be the one in this spot, and cube root. These are all functions that we've already seen at some point in our lessons in the first part of our first semester of our class. But now we want to take a look at them more in a global sense, take a look at some of the things that happens with all of them and discover what is common among all of these families of functions and what makes them distinct and different from each other. And then once we've understood what the parent functions are, then we should be able to use graphical transformations to graph functions based on the family that they're in. And we should be able to identify the domain and range of a given function based on the transformations. All right, so parent function. A parent function is simply the most basic function and graph that still has all of the characteristics of graphs in that same family of functions. So if we're talking about quadratics, it is the simplest function and graph that still has all the characteristics of being quadratic. If we're talking about cube roots, then it is the simplest function and graph that has all the characteristics of being a cube root. Okay? So just a quick go through as to what these what these parent functions are that we want to make sure that we understand. The linear function we should be very familiar with. The parent of that is f of x equals x. So no m, no b, just x all by itself. And the domain and range of a linear function is all real numbers. We can use anything for x, we can get anything as an answer for y, or f of x. The absolute value function is the one that looks like a v. The parent function is f of x equals absolute value of x. You'll notice it has a vertex at 0, 0, so that's where the parent vertex is. And the right-hand side has a slope of 1. The left-hand side has a slope of -1. Our domain for absolute value is all real numbers, so again I can take the absolute value of anything, but my range now has been restricted because my v is entirely above the x-axis. So because everything that I get for an answer is up here, and I don't have anything down here below the x-axis, then that means my range is going to be that y is greater than or equal to 0. We do want or equal to because that vertex that's right there does have a y value of 0. So 0 is a possible y value, but nothing below that can be possible. And again, this is just in relationship to the parent functions. The quadratic function, the parent function is f of x equals x squared. Again, the domain for this is all real numbers. I can square anything. But again, similar to our v, the u shape of this graph again stays above the x-axis with a vertex at 0, 0. So my range is going to be y is greater than or equal to 0 because there's nothing from this graph that goes below the x-axis. In the cubic function, we've got f of x equal to x cubed. That's just a simple kind of S-curve with a little shelf there at 0, 0. My domain for this is also all real numbers. I can cube anything. And because I can get both positive and negative answers from this, I can get any kind of number for an answer. So my range is also going to be all real numbers. The square root function, remember this one is like taking a parabola and laying it on its side, but then we're only allowed to use half of that because if we use both halves of the parabola, we do not have a function anymore. It does not pass the vertical line test. So we just use the upper half of that parabola shape, which means that we actually have a endpoint, a point where the graph starts. And that endpoint in the parent function of f of x equals square root of x is at 0, 0. So that means both my domain and my range are going to be restricted. My domain is only going to be x values greater than or equal to 0 because my graph is only over here on the right side of the y-axis. And my range is going to be y is greater than or equal to 0 because my graph only goes up here above the x-axis. So I have nothing over here to the left, I have nothing down here underneath, and so both domain and range are restricted for the square root function. And then the cube root function, again, the most simple function is simply the cube root of x. And we've got that shelf again happening here at 0, 0, but it's more of a vertical shelf rather than a horizontal shelf. Our domain is going to be all real numbers, as is our range, because again, I can take cube root of negative x's, and I can get negative answers from that. So all real numbers for domain and range on the cube root function. So these parent functions, you need to know. You need to be able to identify them. You need to know what the basic graph looks like for these parent functions. You need to know what the domain and the ranges are for these parent functions. These you have to know because these form the basis of other graphs in the same family. And the one way to get those other graphs is by doing what's called graphical transformations. So these are things that we can do to one graph or function to create a new graph or function. Okay? There are different ways that we can change one graph and create a new one. One way is to translate it. That's what happened in the calculator activity when you changed your h value or changed your k value. You're keeping the same size and shape of the graph, you're just moving it to a new location. So translating a graph simply means you're moving it around. Reflecting a graph also keeps the same size and the same shape, but you are reflecting it through one of the axes. So you saw that when your a value in the calculator activity became negative, then you get a reflection through the x-axis. And then you can also do a stretch or a shrink. And in this case, the size and shape of the graph does change, either by vertically or horizontally stretching or shrinking the first graph. Okay, so those are three terms you need to be familiar with: translating, reflecting, and then stretch. Transformed function looks like this. So we're saying that we want to start with a function f of x, and we want to create a new function g of x. And we can do that by inserting different numbers in different places and doing different things with it. So we've got the a out here in front. That is in front of this function, and that is being multiplied. So a is always something being multiplied out in front. The h right here is something that's being added or subtracted on the inside of the function itself. So it's usually right there with x, and it's before any squaring or square rooting or absolute value happens. It's inside of that type of function. The thing with this that we need to recognize is the fact that minus is part of the form. So when we're trying to identify our h value, we need to keep in mind that having minus here actually gives me a positive h. And if this was positive, then that would mean h was actually negative, so that the minus negative would turn into a positive. Okay, and then we also have the k, which is also being added or subtracted, but it's on the outside of the function. Usually it's at the end, although sometimes you'll see it happen at the beginning. But again, it's about the fact that we're adding or subtracting this number and not multiplying it that distinguishes it from a. Okay? Can be used, but we're not going to use b at this point. That's something that a, h, and k as numbers that will cause transformations for us. So as I hope you saw in your calculator activity, the h value is going to move your graph left or right. It's going to go right if our h is positive and left if our h is negative. And then a kind of serves two purposes. If the a is negative, something less than 0, then that tells us our graph is going to be reflected through the x-axis. We can also look at a in terms of the number itself. So ignoring the negative sign and just looking at the number. And the mathematical way of saying that is taking the absolute value of a. And if absolute value of a is bigger than 1, then we're causing a vertical stretch. So we get a graph that's going to be narrower than the original graph, the original parent function. If our absolute value of a is somewhere between 0 and 1, then we have a vertical shrink. And so our graph will end up being wider than the original graph, the original f of x graph. All right, so let's put some of this into practice. We have an f of x parent function of x squared. And we want to create a new g of x function, which is x minus 3 quantity squared plus 2. Okay, so let's start by thinking about the parent. This is what the f of x equals x squared graph would look like. This is what we saw just a couple of minutes ago. This is what you should have seen in your calculator activity. Okay, now in order to know how to change this graph to become the g of x graph, we need to identify our a, h, and k values. So for a we said was the number that's multiplied out in front. Since there isn't anything there, we assume that that's going to be a 1, and an a value of positive 1 is going to have no effect in terms of reflection or in terms of stretches and shrinks. Our h value is going to be right here. And again, we said if it's negative here, then that means h is actually a positive 3, because the negative is part of the form. And so a positive 3 tells us we need to move our parent graph 3 units to the right. And then we've got our k value, and that's going to be out here. And for k, it is what it looks like. So positive 2 for k means we're going to go positive 2 here, and that tells us that my parent function, the blue parabola I'm looking at right now, also needs to be moved up 2 units. So when I put all of that together, I can take this parent function that I'm looking at for x squared, and I can come up with what the new graph for g of x should look like. I've gone my 3 units to the right, 1, 2, 3. I've gone my 2 units up, and that gives me my new vertex point. That's the easiest point to start with because it's a significant point on this family of graphs. All quadratics have a vertex. The vertex is a significant point. So that's sort of the first point to do your transformations with. And then you can put in the rest of your points from that. So the fact that I've got points here and here means that from this new vertex I would have a point here and here. Okay, so again, size and shape is not going to change. I'm just changing location because my h and k values simply change location. They are transformation numbers. Okay. Now that I know where my new g of x function should go, I need to identify the domain and the range. Okay, so again, think about your parent first. What was the domain and the range for our x squared parent? And that was that the domain is all real numbers and the range is y greater than or equal to 0. So now if you think of what effect h and k are going to have on that, because the domain was all real numbers to start with, moving it somewhere else doesn't change the fact that I can still use everything. So my domain is still going to be all real numbers, even though I slid everything to the right 3 units. But with my range, because my range was restricted in my parent function, moving it around could affect it. And indeed, in this case, it does. The fact that I've moved my original parabola, which had a vertex at 0, 0, the fact that I've moved that up 2 units means that my lowest y value now is a 2 instead of a 0. And so my range now is that y is greater than or equal to 2 because the parabola goes up from that y value of 2. So because I have a restricted range in my parent, the k value is going to affect my range, and my range is now going to be y is greater than or equal to that k value, which was 2. So anytime you have unrestricted domain or range, namely all real numbers, any kind of transformation doesn't really change that. But if you have a restricted domain or range, then you have numbers, a, h, or k, that could possibly affect those intervals. All right, let's take a look at another one. Here we're starting out with the parent, f of x equals square root of x. We want to change that into g of x equals -2 square root of x plus 1 plus 4. So again, the first thing is to think about what does the parent look like. So we are starting with an endpoint at 0, 0, going through points like 1, 1, 4, 2, and so on. Then we want to take a look at our g function and identify the a, h, and k again. So in this case, I have an A value of -2. Okay, that's my A. I have a H value right here. Since it's +1 on the inside of the square root function, that means I actually had a -1 for H, because the only way I get +1 is if I subtract a negative. And a -1 for H. I also have a +4 for my K value, and that tells me I'm going to move up 4 units. Now let's go back and talk a little bit about that A value. I said that A was -2, and there's two different effects that that number is going to have. The first effect is that we're going to reflect through the x-axis because of the fact that it's negative. The second is that if I take the absolute value of A, that's the absolute value of -2, which is 2. And that is bigger than 1, and so that's going to cause a vertical stretch. So it basically means that every answer that I originally got from taking the square root is now going to be multiplied by 2. It's going to be 2 times as much. So when you go to actually graph this, you want to apply your changes in alphabetical order. So the first thing I want to do is to reflect through the x-axis, because that's an A value, and I want to deal with A first. So if I just did the reflection, my graph would now look like this. Okay? Then I'm going to take care of the other part of A, which is to stretch it. So everywhere where I had a particular answer, for example, when I have 1, -1, I'm now going to double that and make it 1, -2. Where I had 4, -2, it's now going to be 4, -4. Every answer is going to be doubled. And so my stretch now would look like this. Then I'm going to take care of H and K, which moves this graph for me. So I'm now going to move 1 unit to the left and 4 units up. And again, the significant point on a square root function is that end point at 0, 0. So that's kind of the point I'm going to be worried about to start, and then everything else will fit in from there. So if I take my 0, 0 endpoint and I move it 1 to the left and 4 up, I'm going to end up with a graph that looks like this. So now my endpoint starts at -1, 4. I cross through the point 0, 2. I also cross through the point 3, 0. And that takes care of all of the different transformations that my A, H, and K values say have to happen. So this solid orange curve that you see would be the graph of our g function, -2 square root of x plus 1 plus 4. Now, for the domain and range of this, when we think about domain and range of our parent function, you might remember that this is the one function where both the domain and the range were restricted. So if I normally have a domain of x being greater than or equal to 0, but then I move that to the left or to the right because of an h value, that's going to affect the x values I can use. And so my domain now is going to be x is greater than or equal to whatever my h value was, which in this case is -1. So this is saying that my graph starts at an x value of -1 and goes to the right of that. And that's what we see in our orange graph here. Similarly with my range in the parent is usually y is greater than or equal to 0. Well, now I have done two things that are going to affect that. I have used a k value that has moved that up, so now we're going to be comparing to 4 instead of to 0, but I've also had a negative a value that has reflected my graph. So now instead of going up from the endpoint, which would be greater than, I'm now going down from the endpoint. And so my range ends up being y is less than or equal to 4. 4 is because I moved up the 4 units. The less than or equal to is because of the reflection due to the negative a. Okay, so let's just summarize some of these effects that we've been talking about and that I hope you saw in your calculator activity. If you have a restricted domain, then the h value will affect your domain. If you have a restricted range, then the k value will affect your range, as well as if you have an a that is negative. If your domain or your range are all real numbers, then a, h, nor k will change that. You will still keep all real numbers as your domain or range in those cases. All right, so let's see if you can put this together yourself. You want to start with the parent function f of x. You want to use transformations to come up with what the graph of g of x would look like. And I suggest that you approach it in the same manner as what we've just discussed in our first 2 examples. Pause the video for a moment while you try this out, and then come back when you're ready to check your answer. All right, so we again see the parent function in the blue. It has a vertex at 0, 0. It has a slope of 1 on the right side and a slope of -1 on the left side to form that V shape that we know absolute values have to have. And then when we take our transformations in the g function, we can identify that a is 1/2, h is +1, and k is -5. So the a of 1/2, that's positive, so that means my v is still going to open up. But because it is an absolute value of a that's between 0 and 1, I have caused a vertical shrink. So every answer that I had gotten in the parent function is now half as much in my new function. Then I take that flattened out v and I move it down, or excuse me, I move it to the right 1 unit because h was 1, and I move it down 5 units because k was -5. And so the orange v that you see there is the correct graph for my g of x function based on what I know the parent had to look like to start with, and based on the transformations that a, h, and k indicate have to happen. For domain and range, my f of x parent function had a domain of all real numbers and a range of y is greater than or equal to 0. So that means my domain stays the same, all real numbers, it was not restricted, but my range is affected by my k value. So now y is going to be greater than or equal to -5 instead of 0. All right, so that should be enough information for you to be able to work on the problems in the 3.5 practice in your booklet. If you have any questions, make sure you're finding the resources to get your questions answered. Send me an email if you're really having trouble, and we can try to set up a Skype time if you really need to ask some questions. And don't forget to check your completed practice with the answers that are posted on Canvas. I hope that you are able to complete your calculator activity that goes along with this lesson. I hope that this lesson helps to bring everything together into something very understandable so that you have great success with your practice problems as you move forward. And that's it for 3.5. We'll see you next time.